All right. So today we're going to finish our discussion of hemoglobin. We are going to have a quick quiz at the end of class. Your first exam is on Friday. You went to the Seminar this past Friday. I need the email summary by this Friday. And Chapter 5 homework's due Friday. Yes, ma'am.
On the test,
Yeah.
we have to know the amino acids. Do we have to know how to draw them or just identify them?
For this test, just be able to identify them and then tell me if they are polar, non-polar, charged, hydrophobic, hydrophilic. Well, of course you have to know the name. The name and the one-letter abbreviation. Yeah, the one-letter abbreviation, the three-letter abbreviation. Yeah, one-letter, three-letter, name, characteristics.
Yeah, it's like a video game.
We'll work up to drawing them. I know everybody's so excited to talk about hemoglobin. Super, super excited. Any other questions about any of the announcements? Oh, I'm guessing, I haven't written the test yet. My best guess is that's going to be probably a third multiple choice, a third kind of short answer, and a third longer answer. And the stuff that's longer answer are probably like choose two of these three longer questions to answer. So, I haven't quite worked out all the details, but that's my best guess right now.
Like, shorter answer would be like, an equation kind of problem.
It could be like, solve the charge of this amino acid, right? So like you show me some work. Or, which of these two would make a better buffer and why? And then a longer answer would be something about, why can't you have a heme group float around by itself to bind oxygen? That is a longer answer. Or when we look at some of these binding curves, it'll be describe the binding curve of hemoglobin. Good. All right. And I have sorted out all the microphone issues, so all the videos on YouTube for the past week or two should be totally fine to watch, listen to. So, all right. Oh yeah.
Is chapter 5?
Yes. Well, it's going to be the 5 through hemoglobin. So this is whatever we finish on hemoglobin. That'll be the end of chapter 5 on the test. There's a bunch of other stuff on chapter 5, structural proteins. That'll be on the next test. So myoglobin and hemoglobin in chapter 5. Alrighty. So hemoglobin, because we finished talking about myoglobin on Friday. We talked about the heme group, right? That iron is the center of those parole rings. We talked about the myoglobin binding curve. And we started to talk about hemoglobin structure and mechanism. That has 4 polypeptide chains, 2 alpha subunits, 2 beta subunits. It has 2 alpha-beta interfaces. It has 2 alpha-alphas and beta-beta interfaces. The solvent-filled channels are between the alpha-alpha and or the beta-beta. If you are alpha-beta, then it's a hydrophobic channel. So then let's start our discussion about hemoglobin and the structural changes it undergoes. All right. So oxygenation, which, does anyone know what oxygenation means in regular Old English? when it binds oxygen, okay? So binding of O2 by hemoglobin causes extensive quaternary structural changes. There are going to be two quaternary forms that are different for hemoglobin: oxyhemoglobin and deoxyhemoglobin. So the oxygenation of hemoglobin causes a structural shift between the oxygenated and deoxygenated hemoglobin forms. So looking at this figure, which this figure is in your textbook, at least a version of it, maybe not this exact one. We have the deoxygenated hemoglobin up here at the top. So deoxygenated means that there are available binding sites for oxygen. When all 4 binding sites for oxygen have been filled, the structure actually rotates 15 degrees. And so oxygenation, the binding of oxygen to our 4 heme groups, causes a rotation of one alpha-beta subunit to rotate 15 degrees with respect to the other alpha-beta subunit. So right, alpha is a subunit, beta is a subunit. Together they're a subunit dimer, two of them together. And so if this is considered perpendicular and I have my alphas and I got my betas, binding of oxygen causes, they're showing in this case, this set of subunits to rotate 15 degrees from what was perpendicular to no longer perpendicular to each other. So binding of oxygen causes 2 alpha beta, like half the molecule to shift 15 degrees to one side. So, thinking back 2 seconds ago, when I said that the alpha-alpha interface is solvent-filled and the beta-beta interface is solvent-filled, and this picture's a little bit bigger to look at. I was here, I'm now forcing a shift in the overall molecule. It actually is going to force these alpha-alpha interfaces to close up and the beta-beta interface gets closer. So this 15-degree shift actually, we'll say brings the alpha-alpha channel and the beta-beta channel so it brings the alpha-alpha channel and the beta-beta channel to close somewhat. So they were more open, so the binding of the oxygen causes them to close a little bit. Those are solvent-filled channels. So now our solvent-filled channels are more narrow. says a structural change caused by the binding of oxygen. So let's take a look, zoom in on just the heme group and see what happens on the heme group that causes this quaternary structural change. And I realize that it says it's in different colors because I printed in black and white, and probably everyone else printed in black and white. It's not colored. So I will get the colors sorted out for you in just a second. So binding of oxygen, the oxygen binds to the hemoglobin group, or the heme group in hemoglobin. As a starting point, just to remind you. All right, there are two forms of hemoglobin, the deoxy and the oxy, where the deoxy has no oxygen bound and the oxy has all the oxygen bound. Well, they also go by two other names, the T state and the R state. The deoxygenated state is called the T state, where T stands for tight. This is the structural form without oxygen. So in the T state, there are going to be four heme groups with 4 O2 binding sites. Okay, then the other version is the oxygenated state, which is also called the R state, where R stands for relaxed. There's going to be a structure form where all four the heme groups have oxygen bound. So all 4 oxygen sites are filled. So this is going to be 4 heme groups with 4 oxygen bound. Bless you. Lots of sneezing going on today. All right, and as we just looked at in that other picture, the movement between the deoxy form and the oxy form is actually a mechanical motion. Like there's actually a physical shift that happens between the two of them. So the transition between the two states is due to mechanical motion. Okay, does anyone happen to remember from organic how long the average bond is? Typical bond. About 2 angstroms, correct. So it has to be mechanical motion because the subunits are about 30 angstroms apart. So those channels, depending on if they're open or closed, in the range of 30 angstroms. So it can't just be that we're making a new bond or we're breaking a bond, because bonds can only stretch 2 angstroms, and we are 10 times farther away than that. There has to be a physical, mechanical motion happening that causes that change or allows for oxygen to bind. So when oxygen becomes available, one of the deoxy states will start to bind oxygen and start to rotate us into the R state. So how is it possible that one oxygen binding starts this shift of mechanical motion? So let's take a look at my picture over here. All right, so the T state, which is going to be blue, is going to be this guy, that guy, and that. So that's my T state. In the T state, my iron +2, my main guy in my heme group, is located 6 angstroms out of the plane, which means it's 6 angstroms away from being upright with everybody else, which you can see better in my R state. So in the T state, the iron is 6 angstroms down from being in the plane. And that's because my nitrogen porphyrin bonds happen to be too long to allow it to sit vertical with everybody else. So my iron is going to sit out of the plane for now because the N porphyrin bonds to the iron are too long. When oxygen binds, those bonds, these guys right here, this N porphyrin iron bond actually contracts. They actually get shorter. And because those bonds get shorter, now the iron can get up and be in plane with everybody else. So when oxygen binds, the iron porphyrin bond contracts and the iron moves in plane. Those bonds get shorter and the iron can pop up and sit perpendicular with everybody else. This mechanical motion, right, so now the iron was here, it scoots up and now is in line with everybody else, forces everybody else, the next subunit over, to also pull its iron up, which then causes the next one to pull its iron up, which then causes the next one to pull its iron up. So the first oxygen that binds causes a cascade of action around the ring. So you may be thinking, why does adding oxygen to this cause those bonds to shrink? Well, we're in that space, so I'll write it in the back. So it has to do with how many things are stuck to the iron. So in a heme group by itself, how many things are bound to the iron? Anyone remember from our picture the other day? See if I can find it. 5 things. Yep. So we had our picture. Here it is. All right, here's our heme group. A typical iron has the 4 porphyrin rings, like the 1, right, 4 nitrogens attached to it, and the 1 histidine group over here. So typically it has 5 nitrogen-containing groups bound to it. So with no oxygen bound, that heme group, this guy right here, is going to be slightly curved because it only has 5 things bound to it. And that histidine is actually pulling on it a little bit because, right, these bonds are kind of long. These nitrogen iron bonds are slightly on the long side to keep the iron flat in this plane. And so the histidine's pulling on a little bit, so really it looks more like my histidine down here. All right, it's actually pulling it down, so it looks curved. All right, got my porphyrin ring sitting around here, porphyrin ring, histidine, that's my iron. I'll label my iron. Fe2+. My oxygen is now going to be my 6th ligand. So when oxygen binds to the 6th ligand, it is now able to pull the iron back up into the plane because it's the 6th thing, and it actually physically pulls the iron in the same plane as the whole heme group. And as much as the histidine is pulling on it, it actually releases a little bit and lets the iron sit flat with all those other guys. So when oxygen binds, you now have 6 things bound to it. The iron now it becomes planar with this whole heme group. And now you've forcibly changed where the iron is, which then is going to cause a cascade of forcing all the other heme groups to shift where they are in relationship to their group. They all pop up in the space. And when they start doing that, then oxygen can bind even easier. And so one oxygen binds, it forces all the other oxygens to bind. I have a great discussion that I will skip today about high spin states and low spin states and how iron can actually shrink in space. But if anyone's fascinated about how iron works, because it's my favorite molecule, I have like 2 or 3 more pages of notes we can go over later. Note takers? All right, maybe. All right, in that case, let's take a look at what's going on in terms of amino acids. So we got 2 stable positions, right? We got our T state and our R state. We got our deoxy and our oxy state. So the difference really between those states, besides obviously the fact that one has oxygen bound and one doesn't, is the mechanical change that's happening at that hydrophobic interface, our alpha-beta interface. So, I don't know if you caught on, but it's kind of important that there is a mechanical shift between the T and the R, 'cause I've said that probably about 20 times in 10 minutes. So there is a mechanical shift that goes on between the two of them. From one allowed conformation to the other allowed conformation. So there's only really two stable or two allowed positions. And it comes down to looking at our differences in amino acids that we have down here between our T state and our R state. So going on here, we got our tyrosine, right? This is our alpha, and that's our beta, right? We're looking at the hydrophobic channel. All right, so tyrosine, this is showing a hydrogen bond between asparagine and tyrosine. So we're going to have a mechanical shift where the beta is going to shift up, and this guy's going to shift down in the presence of oxygen. And so this hydrogen bond is going to have to break. Histidine cannot make a hydrogen bond to tyrosine. That's not possible. But this asparagine can make another hydrogen bond up here past point 38, kind of up here. Oh, sorry, I mislabeled that. It should be ASN. This molecule can now make a hydrogen bond with that. So there's only two allowed positions. Either here, a hydrogen bond between asparagine and threonine, or up here, between asparagine and up there. So these are the only two allowed conformations because of where the hydrogen bonding has to occur. Why are there not really any charged groups going on in these channels? They're hydrophobic, right? The only really allowed interactions we can have are hydrogen bonds. So this is the only two spots where we can get hydrogen bonds to line up correctly. So then, that's been a lot of discussion about all the different allowed positions and the iron. Let's take a look at what the oxygen is doing in all of this.
So you
Yeah.
said that there wasn't any charge, really because.
It's hydrophobic.
Okay.
It's the hydrophobic channel. So what is the role of oxygen as well as the rest of the molecule? So, right, hemoglobin is really pushing together two different things that are going on there. We got the heme group, and we got the globin, where the globin is the rest of the protein. All right, so we've talked about heme, we've talked about the iron in the heme, so then the globin is all the amino acids that are participating in this also. So they have a few different jobs that they are going to do. First one is going to protect our iron. So what did we talk about on Friday about why can I not have a heme group floating by itself, or an iron plus 2 floating by itself in the presence of oxygen? It'll be permanently oxidized, right? And you don't want that. So in the presence of oxygen, iron plus 2 could be permanently oxidized to iron plus 3. Not good. Iron plus 3 can't bind any more oxygen. So it would happen once, and then that heme group would be useless. Luckily, we have that histidine that we've been talking about. This histidine, right here, so this is my iron group, and then this is my heme. So I got my iron plus 2 sitting in the center, my heme group sitting around there. I have this histidine right here. Oh, there it is. I have my histidine attached to the back side of that porphyrin ring. And the histidine attached to the backside of the porphyrin keeps it in the +2 state. You can see that there's another histidine over here. That is not the same one. I'm talking about this guy over here, this F8 histidine. That's the one that's really the fifth ligand. All right, so some of the important things about globin, besides it's able to protect iron in a +2 state, it has the histidine attached to the backside of the porphyrin ring that keeps the iron in the +2 state. I guess the histidine and the heme group together. The globin, the rest of the protein, has the histidine and the heme group in a configuration that only allows oxygen to enter at an angle. Right, there's no way for the oxygen to come straight into the iron. It's actually going to flow in this way at kind of an angle. Why is that important? Well, what is the main job of this hemoglobin? Bind oxygen and then drop it off, right? It's fine. Like, it could do the first two jobs. It could pick it up and it could transport it around, but unless it's dropping it off someplace, your hemoglobin isn't actually worth anything. So because the oxygen has to enter at an angle, it doesn't bind as tightly, which means you're able to release it, which is good because we want the oxygen to be able to be released. So since it comes in at an angle, it cannot bind as tightly. The oxygen cannot bind to the iron as tightly. Therefore, we're able to drop it off someplace else. Yes?
An arrow where the oxygen is coming in.
Sure.
Like, what are the other amino acids, like that one, right next to where you do O2? Like, where is that attached?
This histidine?
There's like what it is. I think it's tyrosine.
This guy? The one that's kind of floating free? It's actually, so this side should be my beta group. Yep. 9944. Yep. So this is all one alpha group, and this is all one beta group, and this is the channel. That's our channel that the oxygen can float through between an alpha beta subunit. Does that make sense? Yeah, some of these are just free flowing. It's just because they didn't show the rest of the amino acids attaching them. All right, so oxygen comes in an angle, doesn't bind particularly tightly. Who remembers what the shape of the myoglobin oxygen binding curve was? Linear, kind of exponential, a U, exponential. So what do you think the hemoglobin binding is going to look like? Similar to exponential. Let's walk our way through this graph. All right, so relative stability of our T and R states. These first two statements should make sense. So if there is no oxygen anywhere near hemoglobin, it's going to prefer to be in the deoxygenated state. Because of that, that should be the more stable state. Right? No oxygen, it's in the T state, which means it's the preferred state, but should be more stable. All true. If there's now oxygens present, it's going to move to the oxygenated state, which that should be the more stable of the two states. So far, so good? Okay. Lots of blank stares, so just checking. So if I look, here's my free energy. This is big old G. And this is YO2. What's YO2? Right, the likelihood of it binding, it's related to big K. It's only between 0 and 1, where 0 is none bound and 1 is all bound. Okay? So, free energy, if you are in low energy, you are more stable. Sounds familiar, right? High energy is less stable. So if I have no oxygen present, based on the statement up here, T is more stable. Should T have higher or lower energy? Should be low energy. True. Here's my T state. Lower energy than the R state. So no oxygen, which is 0. T should have less energy, which then means more stable. All those facts coming together. No oxygen, more stable in the T state, which means lower delta G. There's that point on the graph. Okay, now I have tons of oxygen. What state am I in? I'm in the R state. If I'm in the R state, should that have higher or lower energy? True. Here's my R. So now my R state, R is of lower energy, which means more stable, which means preferred. Which makes sense, because now I have tons of oxygen. Everybody should be in the R state. You can see that actually my graphs, right, this line intersects with this line, because at some point, I'm either have all 4 heme groups open, or all 4, right, all of them have no oxygen, or all 4 have oxygen. So you have to go through some state where like there's 2 and 2, or 1 and 3, or 3 and 1, some combination like that. So that's what the intersection is telling us, that there's some point at which you shift from 0 to 4, or 4 to 0. Good? So looking at this graph, here's my R state. I've now shifted so that my x-axis is PO2, right? Concentration of oxygen, partial pressure of oxygen. And I still have my same Y0 or YO2, no oxygen, lots of oxygen. So as I go from no oxygen to lots of oxygen, my R state is exponentially going up, more likely to be in the R state. If I'm down here, no oxygen to lots of oxygen, I'm not likely to be in the T state. If you put these two graphs together, an exponential curve and a straight line, you get the actual hemoglobin curve, which is sigmoidal. Makes an S shape. So if I added together exponential plus linear, you get sigmoidal. So it is different than hemoglobin, or it is different than myoglobin. Hemoglobin is a S. Myoglobin is just kind of a like that. So, two facts about this graph, and then we'll take our quiz. Right, so R to T is always in equilibrium. Relaxed to tight, you're always in equilibrium, shifting between the two of them, depending on how much oxygen is available. So at intermediate partial pressure of oxygen levels, you expect to see some of each. There'll be some R hemoglobin, some T hemoglobin. There should be they're both around because you're in equilibrium going back and forth. And if I'm at one of these intermediate PO2 levels, somewhere in here, I expect to, be somewhere in between the two of them. What does this kind of graph look like if I was talking about acid-base chemistry? It looks like a titration curve. It's very similar to a titration curve in that at low concentrations, I am mostly in the T state, and then I reach a point where I quickly convert to the R state, and then I stay in R. And everyone remembers, like, this part of the curve is like where you're in equilibrium, the kind of up and down portion of a titration curve. The exact same thing. That down here, it's similar to T, because it's linear. Then up here, it's more like R. And so this zone in the middle is my equilibrium, where I'm quickly changing from the T to the R shape, because I've reached a critical amount of oxygen that all of a sudden everybody converts. You can either write that all down or just remember that all, but this is similar to a titration curve and how it works. All right.